So let's now combine what we've learned about nuclear stability and the types of radioactive decay and see if we can make a connection within them. I'm going to give you here some examples of radioisotopes that decay via beta emission. Here's one, C14. Here's one, K40. Please pause the video and try to see if you can complete the balanced nuclear equation here. Remember, the total mass numbers have to be the same on both sides. And the total atomic numbers or nuclear charges have to be the same on both sides. Be careful, because beta is a -1 nuclear charge or atomic number particle. Okay, what do we see? All right, this is N14, and K40 gives calcium 40 as its daughter nuclide. Now let's observe what is happening here. Look at the change from C14 to N14. Notice the mass number doesn't change, but the atomic number does. In other words, there has been an increase in a proton without increasing the corresponding mass number, right? So we've increased the number of protons by 1, but if the mass number did not increase, that must mean, therefore, that the number of neutrons must have decreased by 1. So therefore, how do we explain the emission of a beta particle? We would propose, therefore, that a beta particle is produced when a neutron decays to produce a proton and a beta particle. Look at this equation here and convince yourself that it is balanced and that it makes sense. So beta decay happens when a neutron decays into a proton. Okay, let's consider now one that we mentioned but we haven't done any exercises with. Let's try positron decay. Here are two isotopes, C11 and K38. Notice these are different isotopes of the same elements, but in this case, the type of radiation produced is positron particles or positively charged electrons. Please pause the video and see if you can balance those two equations. And then come back and we will see that the daughter nuclides are, for C11, we get boron 11, and for K38, we get argon 38. Once more, let's look at the changes that happened here in the nuclides. So in going from carbon to boron, you decreased the atomic number, therefore you must have decreased the number of protons, but the mass number stayed the same. So if you decrease the number of protons by 1, but the mass number stayed the same, that must mean that you must have increased the number of neutrons by 1. And so we could conclude that when a positron is emitted, what must be happening is that a proton is being converted into a neutron. And that's the equation for the process. So again, beta decay converts neutrons into protons. Positron decay converts protons into neutrons. Now, there is another type of decay that we have not mentioned specifically, but we did mention as a particle that there is such a thing as an electron decay. This happens typically with very unstable nuclei, and what happens is they decay by capturing an electron. Here's argon 37 and iron 55. Now, this is very important. Remember, when we study chemical reactions in the past, we know that we can see atoms gain or lose electrons. And that converts the atom into an ion because it either gains a negative charge or it loses a negative charge. But recall that the electrons that are involved in this type of change are usually valence electrons. The nucleus itself remains the same. Now, when we talk about a beta particle or a positron, we're talking about an electron that was not transferred from the electrons in the orbitals but it was actually a particle generated from the nucleus itself. And as a consequence, you generate a different nucleus, in other words, a new element. So in electron capture, what happens is that the unstable nucleus captures an electron, not likely from the valence shell, but from the inner orbital of the same atom, not from another atom like what happens when you make ions. All right, so that is what is happening here. A nucleus of an unstable isotope is capturing an electron from its own inner orbital and bringing it into the nucleus to generate a new nuclei. Okay, excuse me. Now look at the equation there, and again, I am using the E when I represent electron capture, and I'm saving the Greek letter beta for the beta particles that are released during radioactive decay events. Let's see if you can balance the equation and tell me what is the daughter nuclide in each one of these electron capture events. All right, so we would have chlorine 37 for the first one, and correct, manganese 55 for this one. Again, remember, it's a matter of balancing out the mass numbers and balancing out the atomic numbers or nuclear charges. But again, notice what's happening. In going from argon 37 to chlorine 37, you have decreased the number of protons. Same thing when going from iron 55 to manganese 55. However, the mass number itself stayed the same. So once more, we decreased the number of protons by 1, but since the mass number stayed the same, that must mean that we increased the number of neutrons by 1. And so what we're seeing is that in the case of an electron capture, what is happening is a proton of the parent nuclide is gaining an electron and being converted into a neutron. So similarly to positron decay, a proton is being converted into a neutron here. Of course, we have the other types. For example, we studied alpha decay. We saw this example of the conversion of polonium-212 to lead-208. But again, we can do the same kind of analysis and look at the value of A and the value of Z, and we can see that the on the bottom, polonium going to lead means that you decrease the number of protons by 2, and looking at the mass number, similarly, you decrease the number of neutrons by 2. Well, that's exactly what a helium nucleus is. There's another type of event that we'll talk about a little later, but this is called the spontaneous fission. And here you have a relatively large, unstable nucleus that essentially breaks up into smaller ones, and in the process typically emits other kinds of particles. Now the question is, can we to some extent predict, given a radioisotope, what mode of decay it's going to undergo? Well, we can in some cases. Let's go back to that chart that we did earlier, where we projected for different elements, according to their atomic number or the number of protons, how many neutrons are in each one of their isotopes. And remember that we said that for small atoms, a 1-to-1 ratio of neutrons to protons pretty much is where the stable isotopes are. But as you start reaching the area where you have about 20 or more protons, from that point on, it seems like you need more neutrons than protons, a ratio greater than 1-to-1. Now think about it. Let's say that I have an isotope that is, let's say in this area here on the top. Okay, I'm exaggerating, but let's say we have an isotope there on the top. What does that mean? It means that it has a very large ratio of neutrons to protons. In order for that isotope to stabilize, what it needs to do is it needs to lose neutrons and gain electrons, correct? And so what you need is you need a process that will convert essentially neutrons to protons. Which one is that? Well, as we saw before, this is the process of beta particle decay, where a neutron is converted into a beta particle and a proton. So see, for many of these unstable isotopes, we may be able to predict that it's going to have a beta decay if the neutron to proton ratio is too large. Now, let's look at the bottom part of this graph here. Let's say you have an isotope, and again, I'm exaggerating the position. It's mostly usually like around the periphery of that belt of stability. But let's say that you have an isotope that has a ratio of neutrons to protons that is too small. That means it's underneath the belt of stability. So the event that would favor its conversion would be one that essentially increases the number of neutrons and decreases the number of protons. So what kind of event would that be? Correct. If the ratio of neutrons to protons is too small, you would expect something like a positron decay or an electron capture. So for many situations, like I said, you can probably predict what is going to be the event, the type of decay that an unstable isotope is going to have. Now, we ask these kinds of questions in some very limited scenarios. Most of the time when you're given a problem to solve, let's say, for example, to balance an equation or to make predictions, it's more likely they're going to tell you, well, this is the type of decay that this particular radioisotope undergoes. Okay, so let's go ahead and use this that we just studied here for a little practice. Let's consider the isotope B13. I would recommend right away, go to the periodic table, make sure you know where boron is. Question number 1, is it a stable isotope? All right, so remember, how do we deal with this? Well, we ask ourselves, if it's boron, how many protons would it have? It's atomic number 5, so it has 5 protons. And if its mass number is 13, what would be the ratio of neutrons to protons? Well, that would be 8:5, which is, for a small element like boron, that is in excess of the ideal 1-to-1 ratio, right? Remember that we said that we want to be in a region where for these smaller elements here, you want a ratio of about 1-to-1. And in this case, well, we saw that this is not the case. So what we're going to do then is we're going to have to decrease the ratio. How do you decrease the ratio of neutrons to protons? Again, you come back here to this chart, and if the N to P ratio is too large, that means that you expect for there to be beta decay, as it says here on the top of this chart. So we would expect beta decay in order to lower the number of neutrons and increase the number of protons. So now we know that our parent nuclide is B13 with an atomic number of 5, and the product is a beta particle. So what is the daughter nuclide? Please pause the video and finish it out so you can do this, right? So this is boron 13 emitting a beta particle. What would be the other, the daughter nuclide? Correct, it would be C13. All right. Okay, before we cut off here, I'm going to leave you with one more practice problem, and I'm going to give this one for you to work on. If you have any questions, you can ask me later on. So consider the isotope gold 188. Question 1, is it a stable isotope? Question 2, if not, what type of decay will it undergo? And 3, given the type of decay, what is the nuclear equation? Okay, I'm going to leave that with you. And now we're going to go on and talk about other topics related to nuclear stability, and that is something which is what we call the nuclear binding energy.